Welcome back, guys. This is part 3 of the partial fraction decomposition videos. Gosh, I can't talk today. And it deals with linear factors that are repeated in your denominator. So here is our example problem for linear repeated factors. First, notice we don't have a basic rule for that. We've got a quotient. We've got a polynomial over a polynomial. We definitely can't use u sub here. If you expand this and then take its derivative, you don't get a multiple of what they have up there. So this is not a constant over u du. Since it's not a u sub and it's not a basic rule, we're going to go right to partial fraction decomposition. Also, you should note that if I were to expand this denominator, this is an x plus 2 times an x plus 2 times an x minus 1. Those are 3 factors. So if I multiply all 3 of those linear factors together, I'm going to end up with a cubic polynomial in the denominator. I'm going to have an x from here and an x from here, eventually multiplied by the x from the third factor, the other x plus 2. X times x times x is going to give me an x cubed. So the degree of the denominator is greater than the degree of the numerator, or like we've been saying in other videos, the degree of the numerator is 2, and that's less than the degree of the denominator. So partial fraction decomposition is the right way to go with this, and we don't have to do long division first. So we're just going to start initially by factoring. You factor the denominator as much as possible. And turns out this one's already factored as much as possible. Make sure you check the factors. Sometimes they'll leave part of it factored and then part of it needs to be factored further. X minus 1 doesn't factor, it's just a linear factor. And that is a linear factor squared. So this has already been factored. So we get to skip that step this time. That's nice. And we did check that the degree of the numerator is less than the degree of the denominator. Okay, so after you've done that, you write your integrand with a factored form in the denominator and write down its partial fraction decomposition. Now this is a these are linear factors. If I have a linear factor here, remember in the decomposition, if you have a linear factor, you get a constant over that linear factor. Leave some space, we're going to multiply by something. And then this is a linear factor that's repeated. So we're going to get a constant over that factor to the first, plus a constant over that factor squared. And we stop with the x plus 2 squared. We stop at the second power of that factor because that's an x plus 2 squared. If that was an x plus 2 cubed, I'd also have to add a d over x plus 2 cubed. But thank goodness it's not. It's just it's just x plus 2 squared. So I end up with one term with the x plus 2 to the first in the denominator and another term with an x plus 2 squared in the denominator. Notice also that since these were all linear factors, we just get constants in the numerator for each one. You might say, that's not linear. You're right, when I square it, it's not linear, but it's a linear repeated factor. Whenever you have linear factors, the numerators are all constants. Okay, so we've written down the partial fraction decomposition. And once you've written down the partial fraction decomposition, you want to multiply by the LCD. Now the LCD is always the original denominator. It's not this times this times this. If you did that, you'd have an x plus 2 cubed. That's too many x plus 2's. We only want x plus 2 squared. This is your LCD. If you multiply by an x plus 2 cubed here, you're going to end up with extra x plus 2's everywhere. You're not going to want them. It's going to make everything more complicated. So always multiply by the original denominator. That's your LCD. and then simplify. Okay, so I'm just going to write x minus 1 times x plus 2 squared here. All of that is in parentheses because it's all multiplying those two factors. And then I multiply by the LCD over here. And I multiply by the LCD over here. And I multiply by the LCD over here. And if we've chosen the correct LCD, and we have this time, all of those denominators should reduce. So the x plus 2 squared and the x plus 2 squared reduce, because anything over itself is 1. And this reduce. And this reduce. And this and one of those guys reduces. And this reduce. So we're left with our original numerator. The original numerator from the integrand equals a times x plus 2 squared plus b times the quantity x minus 1 times x plus 2 plus c times x minus 1. I'm going to distribute that c. I have cx. Oh, maybe not. Just kidding. We'll do that later. A different type of problem. Don't distribute. Just leave it like this. Okay, so we multiplied by the LCD and we simplified. Now in the last set of problems we were looking at linear factors that were not repeated, and the way we were able to find the a and b was to choose x values that would make those factors 0. We can do something similar here, but this time we've got 3 unknowns. Treating the x not as an unknown, but treating the a, b, and c as unknowns here. This is one equation with 3 unknowns. We're trying to find the a, b, and c, those constants that we can multiply by so that this actually equals this. In order to find those, we're going to choose x values that make each of the factors 0. And because of the repeated factor, because of that x plus 2 squared, it's not going to be enough. We're also going to have to choose a third x value. But we're going to start in the same way that we started on the last set of problems. So choose x values that make the factor 0. You're going to substitute and solve. For a and b, or b and c, or a and c. It's going to be one of those combinations. And then I'll tell you what to do to get the third constant. So let's see. First, I want to choose an x value that makes this 0. Well, if x equals -2, that would be 0. And then I'm substituting -2 into both sides of this equation. -2 squared is 4. 4 times 2 is 8. So I've got 8 minus 21 times -2 is -42 plus 22. And that equals a times 0 squared, so that's 0. And if x is -2, that's 0, so that guy's gone. And over here, I've got c times -2 minus 1. -2 minus 1 is -3. So let's simplify this a little bit. -42 plus 22 is -20. And -20 plus 8 is -12. So I get -12 equals -3c. So we're going to divide both sides by -3, and we get c equals 4. All right, so we got one of our 3 constants. We got c. By letting x equal -2, which makes that factor equal to 0. Now I need to choose an x value that makes the x minus 1 equal 0. Let's try x equals 1. When x equals 1, we get 2 plus 21. That's 23. 23 plus 22 is 45. And that equals a times 1 plus 2, that's 3 squared. 3 squared is 9. And if x equals 1, this is b times 0. If x equals 1, that's c times 0. So that guy's gone and that guy's gone, and that's our whole equation. So we can solve for a. Isn't that nice? A turns out to be 5. Okay, now because of the repeated root, because of that repeated linear factor in the denominator, we're not done yet. I found a and I found c, but I wasn't able to find b. When I let x equal -2, that was gone. When I let x equal 1, that was gone. So both times b was gone. I need to choose an x value that won't make b disappear. Unfortunately, it's not also going to make this a and c term disappear, but you can pick any x value you want. You want to pick a convenient x value. Since we had 3 constants, you're going to have to choose 3 x values. You want to choose those x values, like 1 for each factor, and then if there aren't enough factors to go around, like in this case, you're going to choose another convenient x value. I think the most convenient one is x equals 0. So I'm going to substitute x equals 0 into both sides of the equation. It's plugging in 0 is really easy. So I've got 0 plus 0 plus 22, so I've got 22 on the left, equals a times 2 squared. 2 squared is 4, so 4a, plus b, and this is, if x is 0, -1 times 2, so that's -2, plus c times -1, or you could say minus c, same thing. So I've got one equation with 3 unknowns, but I already know what a is and I know what c is, so I can substitute those in. A is 5, and c is 4. So I've got 22 equals 20 minus 4, so 16 minus 2b. Subtract 16 from both sides. Bam, bam. All right. We get 6 equals -2b. Isn't that nice? Works out. Turns out that b equals -3. Okay, so we had to choose x values that make the factors equal to 0, substitute and solve. And when we ran out of factors, we had to choose another convenient x value. Usually you're going to choose something like x equals 0 or x equals 1, or sometimes x equals -1, something like that. If you're looking for 3 constants, you're going to have to make 3 choices for x. If you were looking for 4 constants, you'd have to make 4 choices for x, and so on. Okay, so we're here. Remember why we did all this. Like, what was the point of this again? A, B, and C, those are numbers. Those are the numbers that we need to choose so that this plus this plus this equals this. As long as all of our algebra is correct, I claim that if I plug in a equals 5 and b equals -3 and c equals 4 over here, the black expressions, before all those cancellations, before everything we did to them, we're going to get the original integrand. So according to partial fraction decomposition, according to our method, according to our algebra, according to our procedure, this is equal to this. It was a over x minus 1 plus b over x plus 2 plus c over x plus 2 squared dx. And now we want to substitute back in. So I'm going to call this step 4. Substitute a, b, and c. Into the form of the partial fraction decomposition. My marker's given out on me. Use purple now. and then we'll antidifferentiate. All right. A was 5. B was -3. You could call that -3 if you want to. I just wrote plus -3 because I'm just plugging B right in. And then C turned out to be 4. Now, I've got a rule for that. That's just a log. I'm going to do a U sub and then I'm going to have a logarithm. That one's just a log. And that is an x plus 2 squared. Since that exponent is not a 1, I'm going to bring that up to the numerator. I'm going to call that u to the -2, and we'll use u sub in the power rule for that one. I'm going to do the same u sub for these two guys, so I'm going to split this up into 2 integrals, one for that one, and then one for these two, because it's the same u sub over there. All right, that's my plan. Let's do it. So I've got 5 over x minus 1 dx, and over here I've got -3 over x plus 2 plus 4, and I'm going to bring that up to the numerator. That's x plus 2 to the -2 power. And remember, you say, how can you do that, Miss Townsend? Well, if I've got 1 over x to some power, it's x to the same power but negative. And if you've got a 4 over that, it's the same thing. You're just going to pull the 4 out, like we did here. Okay, so I'm going to do a u sub here, use my denominator. Derivative of x plus 1 is just 1, so du is 1 dx. So this ends up being the integral of 5 over u du, and the antiderivative of 5 over u is 5 times the natural log of the absolute value of u, plus c. We're going to let this guy take care of the plus c. And then don't forget to back substitute. Use x minus 1. All right. And then over here, I have a different u. On this one, u is going to be x plus 2. So that's my u, and that's my u. Derivative of x plus 2 is just 1, so I get 1 dx. So this can be replaced by du. So my integral, entirely in terms of u, is -3 over u plus 4 times u to the -2, all times du. I just left a space to write in my u's, my du. Okay. Now we antidifferentiate with respect to u. So I get -3 times the natural log of the absolute value of u. Over here, bring your 4 down. Add 1 to the exponent. Excuse me. And then divide by the new exponent. And then don't forget to add c. And then we'll back substitute. U was x plus 2 this time. Now this is a -4. And you can write that as -4 over 1 times 1 over u, where u is x plus 2. You can skip that step if you want to. I'm going to clean this up a little bit. Alright, and I get this. So that's our answer. If I take the derivative of this using the chain rule, and the derivative of log of x and the derivative of x to the -1 or u to the -1, if I take the derivative of this, I get this. Then if I get a common denominator on this, it's equal to this. I'm not going to check it this time, but trust me, it checks out. You can also use Wolfram Alpha or some kind of computer algebra system to check your algebra, but this is equivalent. Now, if you're checking your answer in the back of the book, or you're using a computer algebra system to evaluate this antiderivative, the answer might not look like this. The answer might look a little different. Using log properties, we can simplify this. I can bring this 5 inside and this 3 inside and make them powers. So this is going to be x minus 1, an absolute value to the 5th, and this will be x plus 2, an absolute value to the 3rd. And that's because I'm using this rule. If I have a n times natural log of a, that's natural log of a to the n, you can bring that n inside and make it a power. And this is a difference of 2 logs now. Back in algebra you learned that log of a minus log of b is log of a over b. So that's my numerator and that's my denominator. So you might see the answer written like this. My numerator has an x minus 1 to the 5th in it, and my denominator has an x plus 2 quantity cubed in it. So you might see this version, or you might even see the version where the x minus 1 to the 5th has been multiplied out, or the x plus 2 cubed has been written as x plus 2 times x plus 2 times x plus 2, and then they distribute, and then they have this cubic polynomial in the denominator. All of these expressions are different ways of stating exactly the same thing. This is fine for our tests and quizzes. If you want to go further, if you want to check your answer, you can do this. The other log property that comes up often is log of a plus log of b is log of the product a times b. So keep that in mind. Now remember the point of this video as compared to the last video. This was dealing with repeated linear factors. Since I had a repeated factor when I was solving for a, b, and c, at this step right here, after I multiplied by the LCD, when I was choosing the x values that make the factor 0, I only had 2 x values that would make the factor 0. When x is negative 2, that one's 0. When x is 1, that one's 0. But that wasn't enough to get me my a, b, and c. It only got me my a and my c. Unfortunately, I was only able to get a and c using those. That's going to be enough if you don't have any repeated factors. But since we had a repeated factor, we had an x plus 2 squared, it wasn't enough. We needed another x value. Since I'm looking for 3 constants, a, b, and c, I needed to use 3 x's. This one and this one were good ones to go with because they immediately got us a and c. This one was just any old guess. I could pick any x value I wanted. And since x equals 0 is very easy to simplify, I chose x equals 0 over here. So with x equals negative 2 and x equals 1, I got a and c. With x equals 0, I got this equation involving a, b, and c. And then I was able to plug in my a and my c to get b. So this is what will happen whenever you have a problem involving linear factors where some of those linear factors are repeated. There are no irreducible quadratics in this original denominator. If I have an irreducible quadratic, I've got to do something else entirely. And that's for the next video. Thanks, guys.